So the snowpocalypse set us behind. I was a little bit behind before the snowpocalypse. Now we're pretty far behind. We lost essentially a day and a half, 2 days this week. So we do have to kind of go pretty swiftly here. So that's why I had you watch the videos on Ampere's law and the Biot-Savart law to determine the magnetic field strength due to a current carrying wire, and then due to a solenoid, which is just a current carrying wire configured a certain way. And so I'm just gonna elaborate on some points here, fill in some gaps that may exist, and then we're gonna work on the quest assignment for Ampere's law and the Biot-Savart law. After that, all we have is electromagnetism, electromagnetic induction, and then another type of circuit, which uses something that we'll start talking about today. Okay. So what Ampere's law and the Biot-Savart law both do is they determine magnetic field strengths due to current carrying wires, right? That's what you watched in the videos. The Biot-Savart way, the Biot-Savart law is the brute force method, right? That's where you have some nasty integrals that can end up being very difficult. I actually had Logan not go to the assembly yesterday, and he came to class, and we hung out up in Mrs. Ensley's room. And we went over using the Biot-Savart law to calculate the magnetic field due to a straight current carrying wire. And because Dan Fullerton, when he does it, he integrates with respect to theta, which makes the integral a little easier to do, but it's conceptually setting up the integral I feel like is a little more difficult. So we actually did it. We integrated with respect to x, and you get the same result. Okay, you get the same result. So if you're interested in that, I can show you my solution for it, and you can just take a picture of it if you want. But then you learn that Ampere's law does the same thing, but it makes it much easier, right? It was like when we were first determining electric field strengths due to extended charge distributions for things like rings and sheets and lines of charge and things like that. And it was super complicated, and we had to look up integrals and tables and stuff. And then you learn Gauss's law makes that process a lot easier. That's essentially what Ampere's law does for magnetic fields due to current carrying wires.
So is there any benefit to using the Biot-Savart?
You can only, just like Gauss's law only works for at least until you know vector calculus. It only works for very symmetrical situations. Ampere's law will not be applicable in certain situations when you don't have the symmetry. When you can't draw an Amperian loop, so instead of a Gaussian surface, we're going to be dealing with Amperian loops. When you have an Amperian loop that's essentially not a circle or a square, or a rectangle, then you can't use Ampere's law. Okay. All right. So what Ampere's law, and so I'm going to skip the Biot-Savart, right? That's what Dan Fullerton talked about. But when you use the Biot-Savart law, you realize that the magnetic field due to a current carrying wire is, and this is something that you probably want to commit to memory, it is mu naught times I over 2 pi r, where r is the radius of your Amperian loop. Now, just like a Gaussian surface doesn't exist in physical reality, neither does an Amperian loop. But if we're interested in, say, the magnetic field strength at this point right here, right? Well, that point is going to lie on the radius of the Amperian loop that we're going to use. Okay, and so that's going to be distance r from the center of the current carrying wire. Okay, this is not on your formula sheet. You can do the nasty integral using the Biot-Savart law to generate that equation. Or you can use Ampere's law and make it, and Ampere's law, if you know how to do it, and if you've got some practice with it, Ampere's law, you can derive this in half a minute. So it's really not that bad.
What's the difference between the one with 2r and the one with 2 pi r? Because in the video he did both, and I'm not sure which one.
Whenever you use Ampere's law to determine if you have a loop, say you have a loop of wire, and so you have the current going around this way, when you integrate dl, you get the circumference of the loop, right? And so on the left side of Ampere's law, you're going to have 2 pi, right? And yeah, the pi's are going to end up canceling.
Yeah, a straight line is the one that's 2 pi r.
Yeah, this is for a straight a wire.
Okay.
Yeah, a wire that's in a straight line. Yeah. Good question. Okay. So let's say, and here's the same diagram, right? I got the same diagram over here, so I can erase this. Just to show you, because I want to make sure that we understand how Ampere's law works. Because you use Ampere's law way more often in the Biot-Savart law. We got this guy. And the Ampere's law says that the closed loop integral, now it's not a closed surface like a Gaussian surface, it's a closed loop. So you might write like this. It's not written on the formula sheet like that, but if you want it, that's what the little circle stands for. In this case, it's a closed loop, not a closed surface of the magnetic field, dotted with the dl, and dl is now not a segment of wire, right, that carries current. It's just an infinitesimally small segment of our Amperian loop, okay? And you want to orient it. You can integrate both ways. You can integrate dl this way. You can integrate dl that way. Go in the same direction as the magnetic field. Just makes your life easier, right? So I'm going to make my dl point this way. And so b dot dl is just b dl cosine theta. And if dl is always in the direction of b, then b dl cosine theta is always just b dl. Okay. So if that's true, and then Mr. Fullerton showed that that's equal to mu naught times the current that is penetrating the Amperian loop. Okay. So this is Ampere's law. It's written like this on the formula sheet. And I think it's just mu naught I. Mu naught, by the way, it's the permeability of free space. I get those two mixed up. What's that?
What's the difference?
One deals with electric field lines. One deals with magnetic field lines.
So why are they
Is
different?
it the same?
I have no idea.
Is it like the same concept behind it?
Yeah. Like epsilon naught is how easily space permits electric field lines to exist, and then mu naught is a measure of how a vacuum allows magnetic field lines to permeate it. I don't know. One thing I do want to explain for those of you that are going to go to higher levels of mathematics. A closed loop, and Dan Fullerton doesn't go into this. Walter Lewin, if you watch his lecture on this, he definitely does, because this will segue into higher levels of mathematics when you're dealing with things like complex analysis and contour integrals and residues and poles and stuff like this. The Amperian loop is drawn, and then a surface is attached to the loop. So this is what Walter Lewin does. He takes a bag and he puts it around an actual loop. So usually, and this will apply whenever we start talking about electromagnetic induction, usually you just say that it's a flat loop and the surface that's attached to it is just a plane, right? The plane lies within the loop. But it doesn't have to be. Essentially what I have is an open surface, right? A surface that's open on one end that is attached to a closed loop. And whenever you learn, I think Stokes' theorem or Green's theorem in third semester calculus, you'll be like, this will ring a bell. This right here will ring a bell, and you start thinking about it. So understand, though, that it doesn't matter what orientation the open surface has. If I have currents going in this opening, it's got to come out through this surface that's attached, right? Otherwise, it has to end up coming back out the way it came in, and then you have no net current penetrating the surface, because you have a positive current coming in, you'd have negative current coming out, total current 0. Okay, so you're not going to need that for this class too much, but this will ring a bell whenever you get to third semester calculus and you're like relating, integrals over closed surfaces or open surfaces and the quantity of stuff that goes through the closed loop that bounds that open surface. Okay, yes. What?
One question I just had because I just forgot watching the videos is what is mu naught?
It's the permeability of free space. It's like epsilon naught before magnetism.
Okay.
Yeah. It's a constant that they've known for a long, long time, experimentally measured.
Do we know the value of it?
It's like,
Are we supposed to remember it? Is what
it's on your formula sheet.
okay.
You don't have to remember it though. It's just a constant. It's like involves pi too. It's like 4 pi over 10 to the 7th power or something like that. I don't know. I don't know. Gianni knows. That's Gianni.
Hey, Yanni.
Tell us all about
No, it's 4 pi times 10 to the negative 7th. So something like that, approximately. Okay, so again, we set up in this class. Our Amperian loop is always going to be pretty symmetrical, and so B dot dl in this case, B dot dl is B dl cosine theta. Scalar, right? The dot product always gives you a scalar. Dot product of two vectors gives you a scalar. So it's B dl cosine theta. You don't have to say magnitude like you have to say when you're dealing with the cross product. But the cosine of the angle, as I do that integral over this entire Amperian loop, is going to be 1. And so this left side just becomes the integral over the closed loop of B times dl. That's going to equal mu naught times the current. And the current penetrating that Amperian loop is simply the current in the wire. So I can just put it as I. Notice that if I have a circle concentrically or configured around the wire, then the magnetic field is going to be constant. By the way, you did see that the magnetic field is inversely proportional to the square of the distance. So just like electric fields, just like gravitational fields, gravitational forces, sound, light, intensity, almost anytime some physical property falls off or spreads out into three-dimensional space, its magnitude diminishes according to an inverse square proportion. What?
No, yeah. R is equal to the square root of 1 over B. Or like
It's proportional to it, not equal. You got to have an equation for B. That's a proportion. Okay, so B is a constant. What I'm getting at, pull it out, times the integral of dl equals mu naught I. Again, the calculus is easy. When I add up all these dl's, what do I get? L. Or in this case, 2 pi times r. And then you divide both sides by 2 pi r and you get that the magnetic field strength is mu naught I over 2 pi. Now to arrive at this, we had to first use Biot-Savart law to prove that the relationship between the magnetic field and the current, but then we can extend that and say that, well, now the integral of B dot dl has to equal mu naught times the current. Okay. So that's how we get it for a line of charge. Something else that Dan Fullerton did not talk about, he did talk about this. He did talk about, well, that's the magnetic field outside the wire. But the magnetic field also exists within the wire. Just like when we have a charged solid sphere that is insulating, so the charge does not just immediately migrate to the outer shell.
So that current flows on the outside of the wire.
In this class, no, it flows throughout the whole wire, but it's not the same rate throughout the whole wire.
Yeah, it's like, if I remember reading somewhere, it's like 97% of it.
Yeah, but not all of it. And yes, if you're an electrical engineer or a physicist that deals with that kind of stuff, you'll learn how to deal with the minutia there. But in this class, when we have situations like this, usually you assume that the current is constant throughout the entire area, the entire volume. Realistic, no, but as far as learning the physics, the basic physics that describe it is essential. Unless you're like Alex and you're a super genius, you can just dig right in. Okay. So what if we want to know, what if that current is uniformly distributed throughout this area, right? So if I was to draw a small area here, I have the same amount of current as I would if I drew an area there or right in the center, right? Then I have constant current density, right? And then I would still draw an Amperian loop in here, and I would still use Ampere's law. However, in this case, the current penetrating that Amperian loop is not the total current in the wire, right? And that's where Mr. Fullerton kind of went kind of fast, I feel like. Just understand that you can define current density as a vector, current density J, as the amount of current, and we don't really need to ignore the vector stuff for now, current per unit area.
Yes, current density J, because both current and density start with J.
Exactly. Exactly. You're catching on, Trent. You're catching on.
Magnetic field starts with B.
Exactly.
The permeability of fluid starts with mu.
Yeah. As long as you spell it with Greek letters. So if I want to know the total current, I can say it's current density times the area, right? But what you want to do here is just think in terms. I'm not saying you're going to use this, but think in terms of this. J is the current density. So if I was to know that area and the current going through that area, divide it, I get current density. In this class, right? Ignore what Timothy said a minute ago. In this class, we typically assume that the current density is the same throughout. And so the actual current that's penetrating there is going to be the ratio of the areas, right? So I'd say the ratio of this inner area, which is pi r little r squared, over pi, and I'll define capital R as the actual radius of the wire, pi big R squared, right, times the actual current. So as long as the current is uniform throughout the entire area there coming out of the board, then that's how I deal with that's how I get the current that goes in here. We've done similar things when we did Gauss's law, right? We had to do similar things when we had shells surrounded by, or spheres surrounded by shells. So that same kind of thing is coming back, only now we're dealing with two-dimensional planes, right? We're not dealing with three-dimensional surfaces. But it's still three dimensions because current's coming this way and everything that's going on is, in the plane perpendicular to that direction, the direction of the current. Cool beans? Right. This is kind of just review, but I just want to point out some certain things. And if you didn't, I did print the notes. The notes were on the module for a couple days. I think this week and last week, maybe just this week. I'm not really sure. But yeah, you grab those. Okay, this is a coil of wire. And to keep it nice and sturdy and not falling apart, it's wrapped around an insulator, just a piece of PVC it looks like, and then glued down, right? So it's not gonna fall apart. And then you just put connections at the end. So this, all that is a coil of wire. Okay, it's just a wire that's been wrapped up a bunch of times. And a wire that's been wrapped up a bunch of times gets the name solenoid. Now, when you have solenoids that are actually useful for stuff, very often they'll have iron cores put in them. So like something like this will be in there. And remember that video that we watched when you take a magnetic field or a coil of wire, run some electricity through it, it generates a magnetic field. If you put a piece of iron within that magnetic field, then it aligns the domains within the piece of iron, the magnetic domains, and causes it to become an electromagnet, right? You guys know electromagnets, right? You ever play with those as kids? Some of you, maybe. What's that? Yeah. So this is called a solenoid. I like pointing out.
Why is it not a short circuit? Like, why doesn't the current just go straight through the shortest?
Oh, the wire's coated. Yeah, good question. The wire's coated.
Okay.
The wire is coated so that, each loop of wire is in contact with the next, but there's a coating on it that prevents electricity from just going right through.
I finally
Good point.
the term short circuit.
Yeah, I was about to say.
Okay, good. And what's interesting is that if I was to run electricity through this and I got the piece of iron in there as the electricity is going through it, it looks like a short circuit, right? Because it's not going through a resistor, it's not lighting up a light bulb, it's not spinning a motor, but it's really not a short circuit. It's not going to deplete, it's not going to run the battery out real fast because the electrical energy is actually doing something as opposed to just creating heat. It's actually creating magnetic fields, right? And so the energy, yes, it's going to get hot. If I plug this guy in and turn it on for a while, it's going to get hot, but not nearly as fast as if I just took that wire, spread it out, attached the electrodes to the end, and just ran current through that. That's going to get hot way faster. because it's not really generating the magnetic fields within the, it's not doing the work to align the magnetic domains, right, in the piece of iron. That requires energy.
It has no way to transfer energy other than heat.
Wait, say again? Yeah. So if you have a key fob, if you have a car that starts with a key fob, if you have to change the battery, next time you change the battery, what you'll see are the little tiny solenoids with little iron cores in them. And when they're used in circuitry, they're called inductors. You might have heard of induction coils or inductors. So that's what an inductor is just a solenoid. So that's the last part of this class is we're going to do inductor capacitor circuits. Okay.
You know, if you hold it to your chin, the radio waves will go farther, and you can. It's true. The Mythbusters tested it.
Really?
Yeah.
Huh.
Somehow it acts as an antenna.
Interesting. That's bizarre.
Yeah.
Okay. All right. So solenoids, though, I do want to point out. Mr. Fullerton went over this, but I just want to drive the point home. First of all, if I have this configured so that the current's going up on this side and then out on the top and then in at the bottom, then I should get a magnetic field that inside points this way, right? Out at the top, my fingers curl around to have a magnetic field below it that points this way. If it's into the board here, then above it, it should have a magnetic field that points in the same direction, right? So if I was to draw the magnetic field exactly in the middle, it would essentially be horizontal. It would be perfectly straight. We do get little edge effects here. And it will look like a bar magnet, right? Where the fields will exit the North Pole and into the South Pole. However, because, and I'll show you this, it is an approximation, but because this top current that's coming out is creating a magnetic field that points to the left above it, but this one is creating a magnetic field up here that's pointing to the right above it, those fields largely cancel. And so that's why the magnetic field outside of the solenoid is approximately zero. It's not exactly zero, as you'll see. I'll show you. But it's close. It's close, pretty close to zero. Okay. Especially the longer the solenoid gets and the smaller its radius is. Okay. Yeah.
Are the iron bars that are like negating the magnetic field? Is that why, like, if you get too strong of a magnet near an electronic device, it will like destroy it?
Oh yeah. Because electronic devices always have moving electricity. You get a strong magnet next to that, you're going to get magnetic forces on the charges that are in motion. And I don't know the specifics there, but I know bad things happen for sure.
Also, like older, like mechanical hard drives, like they would.
Oh, those are magnetic in nature.
Yeah.
Old hard drives, they literally use magnets. Yeah. Old. They still use them, Timothy.
Well, yeah, but like, that's common in like.
Making me feel ancient.
Like, I mean, I thought one, but like.
I remember 16 megabyte hard drives. Megabyte hard drives.
Floppy disk.
Like the rigid plastic ones, yes, I remember using those. I never used the actual floppy ones, so I'm not that old.
I wonder why they call it floppy disk and they're not.
They're not even, because their predecessors were floppy. Like literally floppy. Okay, so the thing here, and this is where the usage of Ampere's law is a little weird. It's a little weird, so that's why I wanted to go over it again. Again, an Amperian loop is an arbitrary loop, right? It doesn't exist. You can draw it however you want. So I want to know what the magnetic field is inside of that solenoid. So I'm going to draw my Amperian loop like this. Okay. A loop doesn't have to be round. I know loop makes you think round, but it doesn't have to be round. It can be any shape, right? It can be any shape. It can have any orientation of open surface attached to it. It just so happens that most of the time you just want a flat surface, right? It's in the same plane. But the loop, it could look like that. It could be any kind of loop. It doesn't matter. The physics will still work. It'd just be a lot more complicated doing the nitty-gritty. All right. And so around this Amperian loop, I want to integrate with respect to dl. And since the magnetic field points this way, I want dl to point that way here. I must be consistent around the whole loop, so I must integrate, DL must point here, must point to the left, must point there, so I'm just going to draw one of them here. That's DL. And even when you're doing pure mathematics like this, and you're doing these types of line integrals, the directions are very important. The directions, even if they don't represent something in physical reality, they just represent pure mathematics. The directions are very important, and you got to be consistent with the direction. Okay. Yeah, again, you can integrate the other way. That's fine. But aligning DL with the magnetic field is the easiest, most convenient way. All right, and now I have 4 lines, right, that I have to really deal with. 4 lines on my Amperian loop, and I'm going to label them 1, 2, 3, and 4. And I know that Ampere's law states that the closed loop integral of all those b dot dl's for all 4 of those has to equal mu naught times the current penetrating that Amperian loop. And just to get our brains around it, the current that's going into the board on the bottom of all these loops is not going into the Amperian loop, right? The current that's coming out the top side of the solenoid, at least between those 2 edges of the Amperian loop, is going through the Amperian loop, right? So that's the current that we're talking about. We're talking about all these currents that are up here coming out of the board, right? Those are the currents that are penetrating our Amperian loop. All right, and I'm going to choose, again, the Amperian loop is arbitrary, so I'm just going to assign it an arbitrary length, lowercase l. This solenoid will have some length, right? I can measure it easily here. The solenoid has length L. So I'm going to label that L. And then I'm going to use Ampere's law to determine the magnetic field strength right there. It looks weird how you use this square. I remember being confused about this at the beginning when I was learning it too. But you just follow Ampere's law for each line segment of your Amperian loop, and you're good to go. And so I'm going to break it down. First of all, we know b dot dl gives us the scalar b dl cosine theta. Well, for line segment 1, theta is what? Remember, dl on segment 1 points up, magnetic field points to the right. 90 degrees. Theta is 90. So, what? So b dot dl is 0.
So that we can apply that to 3 as well.
Yep. So let's say that. Segment 1 and segment 3. Theta is 90 degrees. So b dot dl is 0 for 1 and 3. So we can ignore it. Segment 2.
Is it not 270 degrees for 3?
Technically, yeah. 270.
Or negative 90 degrees?
Negative 0.
Well, it's also technically 90.
Yeah, because it's this way and that way. So if you're just measuring that angle.
No.
If you want to be specific about your coordinate axes, then yeah, it's 270, but the cosine of 270 is still 0. It's just negative 0. That's a joke for people at home. Maybe not that funny of one. Okay, so number 2, segment 2, the magnetic field is approximately 0. So b dot dl there is also 0. Again, not really 0. But notice the smaller the radius, the more it will be close to 0, right? The smaller the size, the radius of our solenoid. Because this point right here is closer to the current coming out of the board than it is the current going into the board. And so there is a difference in magnetic field there. But again, as I'll show you in a minute, it's not that different. So really all we care about is segment number 4. That's really the only thing that's going to factor into Ampere's law in this case. But I'm still using Ampere's law for a closed loop, right? That I have attached a surface to, but the surface is literally just the plane that is connected by the 4 lines, right? And then I have current that is going through that surface that's attached to that closed loop. And so now I'm going to apply Ampere's law. Really, I don't even need the for there. I have the closed integral of B dot dl is mu naught times the current penetrating that surface, or penetrating the loop, if you want to think of it that way. I know that B dot dl is 0 for the first 3 segments, so the only one I need to worry about is segment 4. For segment 4, I should have done this. My bad. For segment 4, what is B dot dl? BDL times cosine theta, but they're in the same direction, right? And that's why it's convenient to choose the same direction, because then the angle is 0 and the cosine is 1. So it won't be negative 1. Yeah. So it's just BDL. So the left side of Ampere's law just becomes the closed integral of B times dl equals mu naught times the current penetrating the loop. And we're going to assume that the solenoid is sufficiently long so that at least our line segment here is going to have a constant magnetic field. You might say, but you have it almost all the way to the edges. We don't have to. It's arbitrary. We can make it real thin. Real thin. And then the magnetic field definitely will be constant, right? Or at least very, 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 very close.
Infinitesimally small.
Yeah. But I don't want to do that, because I already have something that's infinitesimally small. I don't want to have to deal with it. It's making my brain hurt.
Infinitesimally slightly less small.
Yeah, there you go. No, slightly more. Yeah. Sorry. See, it's making my brain hurt. So the magnetic field is constant, so I can pull that out. Times the integral of dl equals mu naught times the current penetrating the loop. And we'll talk about that current in a second. That's really the hard part of this problem. Because what do I get, as far as what I've labeled on my diagram, what do I get when I integrate all the dl's over segment 4?
You get L.
You get L. So the left side is just B times L. Now how do I determine the current going through that? Because it's not just I. It's I, and then it's another I, and then it's another I, and then it's another I, and then it's another, because you got a bunch of wires. Same wire, but it's carrying that current through that surface over and over and over and over and over again. So how do I deal with that? Well, I have mu naught, so let me just put mu naught there.
Does it have to do with the length?
Yeah. And so solenoids are designed to have a certain number of loops, and that gets the symbol capital N. So I have a solenoid up here that's like N equals 300, I think, and then one that's N equals like 1500. I think it's like something like that. They're not labeled. They really should be labeled, but I couldn't. Yeah. So the thing is, though, is that I can say that the loop density is N over capital L, right? If I have 500 loops here, and I know the length, then 500 divided by the length tells me the number of loops per unit length.
And then
Right.
you multiply the current by that many loops.
Well, I'm talking about this Amperian loop that doesn't have the same length, right? So I have to say the number of loops that are actually putting current through the surface is going to be the ratio of this L to that L times the number of loops times the current, right? So I have mu naught times the length of my Amperian loop divided by the overall length, essentially the ratio, that's saying what ratio of the solenoid is my Amperian loop, spanning, times the total number of loops, right? So if this is 500, and I know the ratio of this length to that length, I multiply it by 500, that tells me exactly how many coils of wire are carrying current through my Amperian loop. And then if that gives me the number of actual wires carrying that current, then I just multiply that by the current, and that tells me exactly how much current is penetrating the Amperian loop. And now that's just I. That's the I that's coming in, right? And this is why coiled wire is so useful. Because you take a wire and have it out straight and run some current through it, very small magnetic field. But then you curl that wire over and over and over and over and over and over again, you just magnify that magnetic field. You concentrate it, right, into the center of the solenoid. Whereas if it was laid out straight, you take this wire, you lay it out straight, it's going to go to from the back of the room, I don't know, all the way out to the parking lot or something like that. And so if you coil it up into something this small, you've taken that entire magnetic field that's generated on that whole length of wire, and you've essentially just concentrated it right here in the middle, right? Yes, it's very useful. Very, very useful. All right. And notice what happens here. And it always happens, just like it did with Gauss's law when we picked an arbitrary sized surface. The little l's cancel. So the arbitrary choice that we made has no bearing. And that's why I'm saying we can make L really, really, really small. A little less than infinitesimally small. Right? I can do that and I'm fine. All right. And Mr. Fullerton kind of stopped here, but he didn't take it all the way to what's on the formula sheet. And so what's on the formula sheet is as follows. So give me another step or two. So the magnetic field strength in the center of a solenoid is going to be mu naught, and I'm going to write it like this, times N over L times the total current in the wire. And then I'm going to define N over L as just the number of loops per unit length, right? N over L is the loop density.
Is there something to represent that?
Yeah, lowercase n. And that's what's on the formula sheet.
Because the lowercase n is in density.
Yes, it's the third letter in density, so that is why, yeah. What's that?
The third letter is the most important letter.
Of course, goes without saying. So my equation for the magnetic field of a solenoid, which comes into play quite often, is mu naught times lowercase n times I. Just know that lowercase n, if you're given a solenoid with 100 loops and you're told the solenoid is 10 meters long, that's a long solenoid, then little n is the number of loops divided by the length.
Say 100 loops.
100 loops, 10 meters long.
That is a thick wire.
Yeah.
That's why either a thick wire
Or it's just very a lot of space between the coils. Yeah.
Don't seem very useful.
Probably not. No. And so I remembered this as the bunny equation. Right.
B uni.
B uni. Boonai. Booney. I'm living in the boonies.
Isn't the mu be pronounced as an N, Ron?
What?
Isn't the mu pronounced as an N?
Yeah, but it looks like a U. Buoni. All right, so that's hopefully if there was anything you need clarification on, hopefully that cleared it up. There is a quest assignment that I'll be doing next Tuesday that deals with some of this stuff. Any questions?
How many questions are there?
How many questions?
Like 15 or something.
Instant zero.
Okay. Any questions?
Good morning, Richmond High School.
Bye-bye at home.
Update. This is a weather update.
Hit like.
due to impending
Smash the like button.